Alright, hello everyone, this is Jonathan with Data Science Castnet. So I recently came across this AI crowd multi-agent behavior challenge and got a little bit sucked in, and I've spent the last couple of days playing around with it. So I thought it'd be fun to kind of document my process as I explore this challenge. I'm going to make one video now, one video maybe midway through the competition once I've had some time to properly experiment, and then one right at the end looking back at what worked and what didn't. Yeah, so hoping that it's going to be fairly interesting. I've been a little bit bored with data science competitions because the sort of standard ones can get quite monotonous in a way. You know, if it's an image recognition challenge, then odds are the winning submission is going to be an ensemble of whatever the latest image classification, ConvNet is. Put a bunch of them together, train them for as long as you can. Maybe do some fun stuff with changing up the data augmentation, but really it's kind of like a fairly well-defined path to winning one of those competitions. Likewise, with a lot of tabular data, you can get creative with feature engineering, but really it's going to be making some good features and putting together, an ensemble of XGBoost or CatBoost or LGBM. So again, there's some room there, but there's also quite a well-defined path. Whereas this one, it's a little bit more interesting because it's not just, oh, I'll just take whatever worked on the previous, image recognition competition and apply it here. So it's a very unique challenge, and for that reason it got me really excited. So let's start with looking at the problem, and then I'll go through the experiments I've done so far and the sort of thoughts and questions that I have going forward. So they split it up into three kind of subsections. They all follow a similar pattern. And so the basic idea here is that you have originally video of these interactions between two mice. And generally I think there's like a resident mouse and an intruder mouse or something like that. And they've got an annotated, I'll just use this diagram here, they've annotated these key points, the ears, the nose, the neck, and so on. And they've done that for every frame of the video automatically. And then they've also had mouse behavior experts, or experts, I think there's a bunch of annotators, go through and for every frame kind of specify what behavior is being exhibited. So they start apart and they have like an other class for just whatever behavior is not one of the predefined types. And then it comes together and it's investigation, and then maybe there's aggression or they're mating or whatever. So the goal is to for every frame to predict those annotations without someone having to do it manually, because it's quite a time-consuming process. So that's the goal, and the data that we get is just a time series of these points for every frame in the video in the sort of video space. So I read through, I had a look at the beginner notebooks, and one of the first things I wanted to do was then find a way to visualize this myself. So this is really messy, but it was just for me to look through some of these sequences, to examine the different behaviors. You can build on this and make it obvious what behavior is being exhibited, but for me I just wanted, first thing right off the bat, A, get familiar with the format of the data, and then B, take a look at the sort of interactions and watch how the sequences unfold. So the data as it comes, for every frame you get something like this, right? So this is mouse 1 and then mouse 2, and it's all the X coordinates in kind of pixel locations, and then all the Y coordinates. And they tell you the image dimensions. I think it's, 1,700 pixels, 1,024 pixels by 570 pixels. So you can go and you can draw those mice. So that's pretty cool. And it was quite tempting to think, okay, what am I going to do? Maybe I'm going to dive straight in. The demo notebooks had like some nice TensorFlow deep learning, sort of really complicated, tons and tons of code. So for me, I always like to, first of all, what's the kind of minimum viable entry for something like this? So the first thing I tried, here you can see there's some different features that I've created from those points. But the first thing I tried was to just create a distance. Take the mean of the locations of all the points for one mouse and for the other, get the distance between the two, and then literally threshold it. If that distance is greater than this, it's one class. If it's greater than 200, it's another class. Otherwise, it's a third class. So pretty hacky approach, but that already gets 75% accuracy. Micro F1 score of 75, it actually turns out they use macro F1, I believe, which is lower, I think something like 0.5, 0.55, somewhere there. So I put this out, I kind of code golfed this down to fit in a tweet, put it out there, and because I was the first to sort of try it out, it was top in the challenge for all of 30 minutes before someone came along with an actual reasonable submission. But it was fun to have my moment of fame, and this is good because this gives me a bit of a benchmark for anything else I'm going to do. If it can't even beat this, which is just literally looking at one feature and a couple of hand-picked thresholds, then it's probably not so good. So that was try number one for an entry. Then I engineered the rest of these features, and these are all pretty trivial. Speed, just looking at the previous frame versus this one, head size, body size, etc. And this is just features for a single frame. There's no treatment of the sequence as a whole. I'm treating each one as a separate observation. Train a really simple classifier on a small subset of the data. And that gets up to 80% accuracy. Precision is also in that range, 0.8. And then the macro F1 score from the competition is again lower. But this is nice. This is like, what can we do if we're not treating this as a time series at all? Just kind of throwing my sort of default tabular classification approach at this. And you can tweak this a little bit. You can obviously add shifted features to start to take advantage of the fact that this is a time series. And without much playing around, I was able to get this entry here. So F1 score of 0.7, precision of 0.8, which at the time was quite high. And one of the things is I'm not skewing these models at all to try and optimize F1. I'm just trying to get accuracy as high as possible, or log loss under the hood. And so that means mine are going to be like higher precision relative to F1 compared to most of the entries on the leaderboard. But still, that was quite nice. That's good to know that a tabular approach can get you. I mean, 80% accuracy is pretty cool. And so let's see, where would that put us now? I think now that the competition's had a bit of time to evolve, the top entries are a little bit higher. But you can see a precision of 0.8 is higher than most. In fact, yeah, this is that entry. I haven't submitted my latest ones yet. Okay, so that was exploring tabular. And again, like that's not an attempt at an entry as much as a second baseline. So first baseline is like, what if I just threshold the distance? Second baseline is, okay, what would a reasonable tabular modeling approach look like? And so that's what this notebook was here, creating a few sensible features, creating a basic tree-based ensemble model, and seeing what that result is. So that was like initial exploration and getting a feel for the data, and also getting a feel for what is a good accuracy, what is a good F1 score. So after that, I started looking, okay, now I want to dive into treating this like a time series problem, and that's the exciting part of this competition. So I loaded up a couple of fast AI-based GitHub repositories. This one looked promising, but then I saw he pointed to TSAI, also great work. So this was fun. This was like some notebooks that I could kind of adapt, start playing around, and it made it really easy to change models. So the nice thing with this guy's work, he's made it so that you can sort of, you can even go, I think one of these notebooks here is like comparing different models. So you can say, okay, let me try inception time, let me try, their sort of default, let me try all of these kind of state-of-the-art models one by one. So let me see if... okay, I can't remember which one it is, but one of these here, there's like a comparing, in the tutorial or somewhere in there. So that was really fun, and that let me start to play around with these models. So obviously, I mean, a lot of these ones, the way they're set up, the idea is that you have a time series as your input, sometimes multivariate, sometimes just univariate, and then as your output you have a single label. Whereas with ours, we kind of want to have labels for every time step. So some of the models I did have to adapt the head or write, like a custom loss function. But still, it was really fun, nice to play around. It also provides, things like Rocket, which is a different way of approaching it. It kind of just takes your data and uses a bunch of kernels under the hood to generate, I think, something like 10,000 or 20,000 features, which you then train a standard ridge classifier on. So that was fun. Rocket didn't work too well on this task, at least the way I tried it. But some of the other models were looking promising. I enjoyed playing around it and seeing which ones did better. Obviously, I don't have any intuition in this space yet, so I was kind of just thumb-sucking, learning rates, using the learning rate finder, but really just guessing in the dark how many epochs I should train for, what changes I should make. But yeah, really fun. One thing I realized though is that, especially relying on someone else's library, which is they've done all the hard work, I really was just playing with black boxes, and I didn't think I could go too much further with just prodding and poking at these models and hoping they did something. So I went back to this first repo, and I stole from one of the files just the bare essentials to get the inception time model running. So you can see here, this is code that I've pretty much just copied and pasted from Thomas's lovely work, and then had to tweak it a little bit to get the outputs working. So I had to write, I played around with a couple of different loss functions, a couple of different metrics. But this is good because this gives me now a model that I understand. I can see how it's built. But it's also integrated with fast AI, and I got the data loaders and everything working nicely. So I get the learning rate finder, I get the schedulers, can do fit one cycle, and while it's training, I get my readouts of the accuracy, but also the F1 score, which is what the competition uses. So this is now like, okay, I've done a lot of experimentation, and I've figured out a sort of direction that I want to explore some more. And that's when it's like, okay, now I can start to buckle down and really, rather than just, playing around, tweaking different parameters, I can start to sort of more formally explore that. And so that's what I've been doing for the sort of second half of the time I've been playing with this, is starting from here, saying, okay, what can I do? What can I do to try and improve this? So a couple of things, and these are all still open questions. One is data augmentation. So the reason I've got these images is that I did also try another approach that people do, which is take the time series, convert it to an image, and then feed it through an image recognition model. So this is one of the attempts at that. So a normal input would look like this, representing 40 frames or 80 frames of the video recorded points, throwing that through an ImageNet pre-trained model. It does okay, but not great. At least not in my testing. But anyway, because I had that, I had some nice visuals for playing around with augmentation. So for example, randomly flipping it or rotating it. And this is a nice, because when you've got this time series, with these models, you're looking at a window within that time series, say 40 or 80 or 120 time steps. So if you go and then take your window of data, and that's one input, and then you advance by one, the next one's going to be very similar, which you don't necessarily want. You want some variety in your training data. And so that's one sort of avenue that I've started to work on now that I've got my model selected. How can I augment this data? How can I take it and shift it around and rotate it and make different variants of it that still represent the original, but without being an exact copy that it can overfit to? So that's one direction. Another direction that I've been playing with is, I really like this model, but in the paper they do say it's a little bit unstable. They advise actually having an ensemble of models. I'm not doing that yet because I feel like that's a nice easy win for the end. But there are some other things I've been able to do. I've, adding a bit of dropout and such helps it during the training, and that also tends to like stabilize it. Some of the earlier kind of, even at a fairly conservative learning rate, it was a bit all over the place in terms of performance on the validation set. But adding some dropout really helps smooth it out. So that's modifying the network itself, data augmentation. And then I think the final part is just going to be kind of exploring how I take the data and represent it in a way that gets fed to the model. At the moment, some models are doing really well, even just taking just the positions, nothing else. But from the earlier tests, like with the random forests and whatever else, you can see that these other features that I created, they actually are kind of useful. I'll put a feature importance plot over here. But they, like the distance between the mice or speeds or, relative sizes, angles, etc. That's useful information. So I'd kind of taken that out for a lot of my testing because it was time consuming. I was doing it on the CPU. So that's the final avenue I want to explore is really, doing some creative feature engineering and pulling out as much information as possible, but doing that, in a way that's really fast. I don't want to wait hours to make my submission. So it needs to all run on the GPU in parallel. So that's going to be the final direction. Yeah, so that's where I'm at the moment. My model is training, is just about to finish making its predictions, so I'll have a score soon, which I'll put up on the screen for like where I'm at with my current kind of hodgepodge of hacked together inception net with a little bit of data augmentation and a fairly sort of small training set. And then over time, I'm going to just explore all those directions that I've just talked about. And we'll come back halfway through the competition. Hopefully, I'll have made some improvements and figured out which of those were fruitful. But yeah, that's it for now. I hope you enjoyed, and we'll see you in the next installment.